So what we discovered so far is there's different forms for a linear equation. There's standard form, slope-intercept form, and point-slope form. M is the slope, B for this equation is the y-intercept. And then we looked at how to derive the slope formula for a line. Given 2 points on a line, we discovered the slope is rise over run. The ratio of rise over the run is the change in y over change in x. All right, so using that slope formula, let's see if we can compute the slope of the line. And we're going to try to find the slope. Okay, we're going to try to find the slope of a line containing these 2 points. -3, -8, and 4, 6. All right, I'm going to call this point my point x1, y1, and I'm going to label this one as x2, y2. Now, in reality, it doesn't matter which point you call your first and second point. So therefore, the slope of this line is going to be change in y over change in x, which is going to be 6 subtract a -8 over 4 subtract a -3. It's going to be 6 + 8 over 4 + 3. So it looks like the slope of this line is going to be 14 over 7, which reduces it down to 2 over 1. So the slope of this line is 2 over 1 here. Okay. Now, if we were to take the time and plot those points in the XY plane, and I'm not going to use a piece of graphing paper to represent that here. I'm just going to do a rough plot here. So -3, -8 is going to be down here in the third quadrant. And then I got the point 4, 6, which is going to be up here in the first quadrant. There's 4, 6. Putting a line to these points, we have the graph of that line whose slope is +2. So therefore, that's saying if you take a point on the line, if you go up 2 units and 1 unit to the right, you'll land on another point on the line. You could do that forever. Up 2, 1 to the right, plot a point. Or you could take a point on the line and instead of going up 2 into the right one, you could just as well go down 2 into the left one. So I could just as well go down 2 units, that's -2, and then to the left one, that's -1. Nonetheless, I'll still land on the same line. So whether you view the slope of this line as 2 over 1 or -2 over -1, it is the same line, the same slope. Okay. We call this kind of a line a rising line in the XY plane. So any line that has this orientation is designated as a rising line. That's to say, as we progress from left to right in the plane, if we rise on the line, the y coordinates are increasing from left to right. We call it a rising line. And as it turns out, rising lines always have positive slopes. Now, if I graphed a linear function in the XY plane, and let's say its graph looked like this. Well, this would not be a rising line. Now, this would be an example of a falling line. And falling lines always have negative slopes. Because as we progress from left to right, we're not rising on the line, we're falling down on the line. Falling. Anybody want to weigh in as to what the slope of a vertical line is in the plane? What the slope of a vertical line would be? Well, with a vertical line, if you choose 2 different points on a vertical line and you move from one point to another point on this line, you're not going to experience any run. All you're going to experience is rise. Okay. So any 2 points on a vertical line always have the same x coordinates. The y coordinates could be different, but the x coordinate is the same. And because of that, if you look at the slope of a vertical line, the x coordinates are the same, and so the denominator of your slope becomes 0. And what happens when we divide anything by 0? What's anything divided by 0? It's not 0. When you divide anything by 0, you get an undefined quantity. So the slope of a vertical line is undefined, because all you have is rise. There's no run, the whole rise. Okay. All right, how about a horizontal line? What would be the slope of a horizontal line? Well, if you have the graph of a horizontal line, all you have is run. You don't have any rise. With a horizontal line, you have nothing but run, no rise. So if you pick two different points on a horizontal line, the y coordinates are going to be the same. The x coordinates will be different, but the y coordinates will be identical. Therefore, if you try to compute the slope of a horizontal line, the y coordinates being the same, you're going to get 0 in the numerator. And what's 0 divided by any non-zero real number? This will be 0. So horizontal lines always have 0 slope. Okay. All right, so here's the possible scenarios when you graph a linear function in the xy plane. It's either going to be a rising line with a positive slope, a falling line with a negative slope, a vertical line with an undefined slope, or a horizontal line with a 0 slope. Any questions about any of this here? It's got to be one of those cases. All right, ladies and gentlemen, let's see if we can graph a linear function here. Specifically, I'm looking at negative 3x plus 4y equals 12. Now, there's many ways to graph a linear function like this. One way is the table method. As the name suggests, we'll make a table. X column, Y column, and then we'll have your ordered pair. Now, we like to normally choose nice values for x, plug them into the equation, and solve for y to generate our ordered pair solutions to this equation. Since you can choose any number for x, you might want to keep the numbers nice. Don't choose any decimals or fractions. And please don't choose numbers for x like 1,000 or negative 1,000, because you're going to have a very difficult time plotting those points. Nice values for x would be maybe like -2, 0, and +2. These are nice values for x. They're close to the origin. So if x is equal to -2, I put -2 in for x, and then I have to solve for y. So we have 4 plus 4y equals 12. Subtract 4 from both sides. We have 4y equals 8. Divide both sides by 4, and x walks out of this with a value of 2. So one ordered pair solution of this linear function is going to be -2, 2. Hence, this is one point that will lie on the graph of this linear equation. Just let x be 0. If x is 0, plug 0 in for x and solve for y. This is gone, and we're left with 4y equals 12. Divide both sides by 4, and y is equal to 3. Hence, here's another ordered pair solution to this linear equation. It's another point that would be found on the graph of that linear equation. Finally, this let x be equal to 2. Take 2, substitute it in for the x variable. And now we're going to have to solve for y. So we have -6 plus 4y equal to 12. Add 6 to both sides. 4y is equal to 18. And that don't look too good. Divide both sides by 4, and we get y is equal to 18/4, which reduces down to 9/2, which for plotting purposes is 4.5.
I have a question.
Yep.
For the -2 one, how did you get 4 when you did -3 times -2?
Let me double check it. -3 times -2, that should be 6, shouldn't it? Yeah. All right. Yeah, that's not correct. All right, so let's do -2 again. Put -2 in here. So you got -3 times -2 plus 4y is equal to 12. So we got 6 plus 4y equals 12. Subtract 6 from both sides. You get 4y equals 6. And then you're going to divide both sides by 4. And you get y walks out of this with a value of 3/2, which is 1.5. Okay. So this should be 1.5. 1.5. Okay. So these are the points we got to plot. We do have some fractions or mixed numbers, but fortunately they're like got a fraction of 1/2, which is easy to plot. It's dead center in between some values. And so now all we have to do is just plot these points, connect them with a straight line, and we'll have the graph, that linear function. And graphing paper, you know, could be used. That luxury. So we take a piece of graphing paper here and we plot these points. So 0, 3, 1, 2, 3, that's my y-intercept. Right there. We'll assume these tick marks are spaced 1 unit apart on both axes. -2, 1.5. -2, 1.5 is going to be right here. And we got 2, 4.5. So 1, 2, now up 4.5. 1, 2, 3, 4.5 would be right there. And it certainly looks like those points are collinear points, meaning that they appear to lie on a line. Being a case, we're going to take a ruler and we're going to put a line through them, and we have the graph of that linear function. Okay, so that would be the graph of that linear function. So that's the table method for graphing a linear equation or a linear function in x and y. And in order to do that, we have to generate some ordered pair solutions by choosing some nice values for x, substituting them in for x, and then solving for y. And then you plot your points that you found, put a line through your points, and you have your graph. That's simple. Okay. That's one way. Another way to graph this linear function is called the slope-intercept method. As the name suggests, we're going to take this linear equation here, and we're going to get the equation into slope-intercept form. Presently, this equation is in standard form. We want to navigate to slope-intercept form, which means we have to solve the equation for y. To solve for y, first we got to move the 3x over the right side of the equation, and we accomplish that by adding 3x to both sides. These drop out, leaving you with 4y. I'm going to spin these terms around. And then I'm going to divide both sides by 4. That means you got to divide each term on the right side of the equation by 4. So we got y is equal to 3/4 x plus 3. And now this equation is in a very special form called what form? That's slope-intercept form. That's in the form of y equal to mx plus b form. Okay. So therefore, I can read off the slope of my line. And the slope of my line is 3/4. And my y-intercept, which is this number b, is +3. That's your y-intercept. Or as an ordered pair, your y-intercept is 0, 3. Now I have a question for you. By knowing the slope of this line and also its y-intercept, do you think that that's enough information for me to be able to graph this line?
Yes.
Should be able to graph it, right? It means I know a point on my line and I know the slope. I know the rise over the run. So that should enable me to, crank out a graph here. Put a particular line there. Okay. And let's see, am I all out of graphing paper? Getting low on graphing paper. In fact, I think I'm all out. So what I will do here is to show you how to graph this using the slope intercept form. I will try to just be as neat as possible here and making an XY plane. I think you'll get the idea. All right, first I'm going to plot my y-intercept, which is 3. 1, 2, 3. So right there, here's my y-intercept at 0, 3. Now my slope is 3 over 1. That means I have a rise of 3 and a run of positive 4. So from my y-intercept, I could go up 3 units. So 1, 2, 3, and then I can go 4 to the right. 1, 2, 3, 4. So up 3, and then 4 to the right. And now I can plot another point on my line right there. So from my y-intercept, I went up 3 and 4 to the right, plot a point. And you could view this slope, instead of being a positive 3 over positive 4, you could view it equivalently as negative 3 over negative 4, same thing. Which means for my y-intercept, I could have went down 3 and 4 to the left. Same thing, same slope, same line. So I could have went down 3 and 4 to the left. So down 3 and then 4 to the left. Plot a point. Notice, point lies on a line with the other points. So it doesn't matter if you go up 3, 4 to the right or down 3, 4 to the left. You're going to carve out the same line. Put a line to these points, and ladies and gentlemen, you have the graph of that linear equation. So that's another way to graph a linear equation, is by knowing its slope and the y-intercept. That's more than enough to generate any number of other points on the line to accurately graph it. Any questions how I graph that using the slope and the y-intercept? And you can do this forever. You could go down 3 more, 4 to the left, plot point. Down 3 more, 4 to the left, plot point. You're going to keep landing on the same line. Or you could do this, go up 3 more, 4 to the right, plot point. So it's up to you, however you want to navigate. This would be the graph of y equals 3/4 x plus 3, or the graph of negative 3x plus 4y equals 12. Any questions how we use a slope intercept method to graph this linear equation? Okay. There is another method to graph this linear equation or linear function. It's called the XY intercept method. All right. Suppose I have an XY plane here and I graph a linear function in it, and suppose the graph looks like this. The point of intersection between the graph and the x-axis has a very special name. It's called the x-intercept. So this point of intersection between the graph and the x-axis is called the x-intercept. The point of intersection between the graph and the y-axis is called the y-intercept of the linear equation. Now, an x-intercept is always a point that lies on the x-axis, and because of that, its y-coordinate has got to be equal to what always? Y has to be equal to what for an x-intercept?
0.
Has to be 0. Otherwise, the point's not going to be on the x-axis. A y-intercept is always a point that lies on the y-axis, and because of that, the x-coordinate of a y-intercept must always be equal to 0. In fact, that's how you find the x-intercept. You always set y equal to 0. To find y-intercept, you always set x equal to 0. So you always set the other variable equal to 0 to find an intercept. That's the easy way to remember it there. Okay. So what we're going to do is we're going to graph this linear equation. Yes, one more time. Negative 3x plus 4y equal to 12. But we're going to graph it this time by computing its x and y intercepts. So let's do the x-intercept first. So how do I find the x-intercept? Well, I let y be equal to 0. That means I take 0, substitute in for the y variable into the equation. And when I do that, the equation collapses down to negative 3x equals 12. Then I divide both sides by negative 3. And out comes my x-intercept, which is negative 4, or the ordered pair negative 4 is 0. That's your x-intercept for that linear equation. To find the y-intercept of this linear equation, we always set x equal to 0. Take 0, substitute it in for the x variable into the equation, and the equation then collapses down. This is gone, collapses down to 4y equals 12. To find y, we divide both sides by 4, and we get y is equal to 3. That's your y-intercept, or as an ordered pair, your y-intercept is 0, 3. Do you think that's enough information now to graph this linear equation, knowing its x and y intercepts and knowing that they are unique points? I think that should be enough information, correct? So therefore, it's very simple now to graph this linear equation. All you got to do is plot the x-intercept, which is negative 4, 0, and plotting the y-intercept, which is 0, 3, taking a ruler, putting a line through these points, and you have the graph of that linear equation. That's the graph. So we graphed it by finding the x and y intercepts. Now, last week on your TI-84, I showed you graphically how to determine the x-intercept by going into your calculate mode with your graph showing and using what function. Does anybody remember the name of the function that we use to find x-intercepts on the TI-84? X-intercepts. We always use the 0 function. The reason why we call it 0 is because we're trying to find an x value for which y is equal to 0. That's why we call it the 0 function, because an x-intercept is really another name for a 0 of a function, because it's a value of x that sends y to a value of 0. The y-intercept was found on the TI-84 by using the value function in calculate. And for the value function, of course, we had to always set x equal to what? 0 in order to identify the y-intercept. Any questions about linear functions so far? All right, let's see if we can apply this a little bit to an application problem. Now, ladies and gentlemen, I said slope is a rate of change, correct? And because it's a rate of change, can anybody name for me an example of a rate that exists in our everyday lives? Some sort of a rate. A rate of change of one variable with respect to another variable. Anybody got an example of a rate? Something per something. Give me an example of a rate.
Miles per hour.
Miles per hour. You get in your car, let's say you drive 60 miles per every 3 hours. That's called a rate, 60 miles per 3 hours. That's the rate of change of distance versus time. That would be likened to what we would call a slope, okay? Specifically, that would be the slope of a linear function that models the distance the car travels versus the time that it's traveling, okay? Any other examples of rates in the real world? Speed, right? Velocity or speed, miles per hour is one good example. Any other examples of any rates? Any rates? Well, we all get on our keyboard sometime during the day on a laptop or a PC desktop, and we type in maybe so many characters per minute. Correct? That's the rate with which we type. Maybe we type in 60 characters per minute or something. Or maybe in my case, more like 30 characters per minute. Accurately. That's the rate with which we type. Okay? In the springtime, if you have a pool, you have to maybe call out a truck to fill up your pool, or maybe use your garden hose. And then you're concerned about the rate with which your pool is filling. In other words, the rate of change of volume versus time, correct, of water. That's a rate. That would be likened to what's called a slope of a volume versus time linear relationship that exists. All right. So slope, ladies and gentlemen, really does have a lot of applications in the real world, because there's a lot of rates out there in the real world. And that's why slope is a very important concept. Now, algebra can address the average rate of change of a variable with respect to another variable. But if you want to talk about the instantaneous rate of change of a variable with respect to another variable at some specific value for the input or independent variable, then algebra fails. You have to resort to another branch of mathematics, which is called calculus. And that's one big reason why the calculus was invented, to give you an ability to easily compute the instantaneous rate of change of a variable with respect to another variable. Algebra can only deal with an average rate of change of a variable with respect to a variable in some sort of an interval. And I'm going to show you that example here. Suppose we have this situation. Suppose a car travels a distance of 20 miles in 1 hour and travels 60 miles in 4 hours. Suppose I want us to compute the average speed of the car. Well, I have two ordered pairs in this reading up here. My x coordinate is going to represent time. My y coordinate is going to represent the distance. So one ordered pair is 1 hour, 20 miles. After 4 hours, I traveled a distance of 60 miles. I now have two unique points, and so therefore I could plot them in my distance versus time coordinate plane here. Remember, the x coordinate is time, the y coordinate is distance, okay? And then I'm concerned with finding the slope of the line segment that connects these 2 points here. So I'm interested in finding the average rate of change of distance versus time on the time interval from 1 to 4 hours. Okay, that's the time interval of interest. To find the average speed of this vehicle on the time interval from 1 hour to 4 hours, we're going to have to find the slope of this little line segment here. To do that, we're going to use our slope formula. I'll call this my first point, this is my second point. Doesn't matter which one you call your first and second point, by the way. Feeding the values into the slope formula, I come out with a slope of 40 miles per every 3 hours, which reduces down to approximately about 13 miles per hour, per 1 hour. So that would be the average speed of this car, 13 miles per 1 hour or 40 miles per 3 hours. So this slope actually has, relevant meaning in our everyday experiences. This is a speed with which this car is being driven, or maybe this would be maybe not for a car. 13 miles per hour, that's kind of slow. Maybe more so for maybe even like a bike. Do you agree? If you're doing cross-country bike riding or something, you could easily ride at that speed, I would imagine. All right. Keep in mind, ladies and gentlemen, this is just the average speed over the time interval from 1 to 4 hours. This is not saying that the speed of our car at every instant in time in this interval is exactly 13 miles per hour. There might be some times when we're, going faster, and sometimes we're going a little slower. This is just an average speed on this time interval. If I wanted to determine the exact speed that my vehicle is traveling, let's say precisely at the 2 hour mark, then algebra cannot deal with that. We would have to use calculus to address that situation, and something called the derivative in calculus, which is the branch of calculus called differential calculus. That would enable me to find the precise speed of my vehicle at any one instant in time within this interval. Algebra can only tell us the average change of distance versus time on an interval here. Okay. All right. But that average rate of change of distance versus time is really the slope of this little line segment here in this distance versus time graph. Did that make any sense there? That example? All right. Okay. What are parallel lines, and what's a characteristic of parallel lines? I think somebody's talking. Sounds a little young in this class. I could be wrong.
It's Riley that's unmuted.
Okay. All right, ladies and gentlemen, parallel lines are lines that never what? Never intersect. Do you agree? In the plane. They'll never cross each other. They'll never touch each other. Suppose these lines are parallel. This is the symbolic way of denoting this, instead of writing the word parallel. What has to be the relationship between these lines? Anybody? How do these slopes have to be related to each other if these are to be parallel lines?
They have to be the same.
That's correct. Parallel lines always have equivalent slopes. Because think about it, it has to be the case, because if the slope of one of these lines is just a little different than the other one, and eventually it's going to run into the other line, correct? It will cross the other line. Slopes must be equivalent for parallel lines. All right, how about perpendicular lines now? Perpendicular lines are lines that do intersect, but there's something special about the way they intersect and what angles they form with each other. What is that angle of interest of perpendicular lines, the angle of intersection? Not just any old angle. It's actually a right angle. Okay, so perpendicular lines intersect at right angles to each other, 90 degrees, 90 degrees, 90 degrees, 90 degrees, 360 degrees all the way around. Right, these are perpendicular lines. So if line 1 is perpendicular to line 2, notice the notation, perpendicular, then what must be the relationship between the slopes of these lines? The slopes of perpendicular lines must be related how? Well, they have to be what are called negative reciprocals of each other. Negative reciprocals. So that's twofold here. They got to be opposite in sign, and they also have to be reciprocals of each other. Negative and then also reciprocals. So that's to say that the slope of line 1, m sub 1, must be the negative reciprocal of line 2. Or synonymously, that's saying the slope of line 2 is the negative reciprocal of line 1. Or another way to say that slopes are negative reciprocals is to say that their product always must be equal to -1. All of these are ways of saying the same thing, that the slopes of these lines are negative reciprocals of each other. Okay? As long as the slopes are negative reciprocals, those lines are perpendicular to each other. They will intersect at right angles. So what happens if I have two lines that do not have equal slopes and also do not have negative reciprocal slopes? Do the lines intersect in that case? The answer is yes, they will intersect, but they just don't intersect at what angles to each other. They don't intersect at right angles to each other. So the slopes of these lines are neither equivalent or negative reciprocals of each other. All right. All right, any questions about parallel and perpendicular lines and how their slopes must relate to each other? All righty, well, let's put that to work now. Suppose that I want to find the slope of a line that is parallel and perpendicular to this line right here. So I want to try to compute the slope of a line that is parallel to this line and then also perpendicular to this line. So what are we going to have to do here? Well, the first thing we're going to have to do here, ladies and gentlemen, is we got to find the slope of this line here. How can I find the slope of this line? And what form is this linear equation or linear function in? What form is this in right now?
Standard.
This is standard form. All right. So what I would like you to do here is you can call this classwork 1. Try to put this equation in the slope intercept form by solving it for y and tell me what the slope of this thing is. So let's try to go to slope intercept form. You guys do that. Hammer that in the slope intercept form. And then when you do that, you tell me what the slope of the line is. We need to know this to answer this question here. Got to know the slope of that line. So go ahead and solve for y. You can call that classwork 1. Today is Valentine's Day, the 14th of February. All right, so let's put that in a slope intercept form. So we got to solve for y. All right, anybody get this?
Yes.
All right, so the slope of this line is positive 2, or just 2 over 1. Okay. Y-intercept is negative 5. So if I am to compute the slope of a parallel line, what must its slope be? Well, the slope also has to be 2, correct? All right, how about a perpendicular line? What must its slope be? What's the negative reciprocal of 2? It'd be negative 1/2. That would have to be the slope of a perpendicular line. Okay. All right, so hopefully you got that there. All right, the next problem we're going to do is we're going to look at one like this. We're going to try to write the equation of the line that contains the point 0, -4 and has a slope of 1/3. And we'll leave our answer in slope intercept form. So we're going to leave our answer in y equal to mx plus b form. All right, now we're given a point on the line and we're also given its slope. That should be enough information to derive the equation of this line, or the equation of this linear function here. All right, well, let's show ourselves how to do that. So we're given the point 0, -4, and we're also given the fact that the slope of this line is 1/3.
Is this also classwork?
No, this one's not. I'm going to demonstrate this one.
Okay.
All right. So to write the equation of this line here, we're lucky here because the point that I give you that lies on the line happens to be what kind of a point? What's so special about this point that we are provided with that lies on this line?
It's a y-intercept.
It's the y-intercept, and we are in business now because that's the y-intercept. Well, heck, look at, they give us the slope of the line and the y-intercept. To write the equation of the line, we can just use the slope intercept form to immediately write the equation of this line. So all we got to do is just drop things in where they belong. The slope is replaced with 1/3. The y-intercept is replaced with -4. Ladies and gentlemen, you got your equation. It's that simple. That's all there is to it. That would be the equation of this line in slope intercept form, because this is your slope and that's your intercept. Slope y-intercept form. All right, we already have it. That was an easy problem. It was an easy problem because this was a y-intercept. Now, we're not always going to be given a y-intercept. We might be given some other point that lies on the line. And we're going to have to take it upon ourselves to find a y-intercept to write the equation of the line. But this was a nice problem because that turned out to be a y-intercept. Okay. Any questions on that one there? So your answer is right here. That'd be the equation of the line. And suppose I wanted you to get this maybe into standard form. Could we do that? I'm just going to demonstrate this quickly here. If I wanted you to navigate the standard form, we should be able to do that. First, I'd probably multiply both sides by 3 to knock this fraction out here. So I'll have 3y is equal to 3 times 1/3 x minus 3 times 4. So we have 3y, the 3's drop here, leaving you with just x minus 12. Then we subtract x from both sides because we're shooting for standard form now. So we'll have negative x plus 3y is equal to negative 12. That is standard form. Just a word to the wise that oftentimes, for whatever reason, authors in algebra books do not like to leave a leading negative sign when your equation is standard form. So we could easily get rid of this -1 here as a leading sign if we just multiply or divide both sides by a -1. And if we do that, the effect is to change all the signs of all the terms. These equations are equivalent to each other, equal to each other. Okay? I'm just saying when you check your answer in the back of your book, your author will probably have it expressed this way as opposed to this way. There you go. We've gone to standard form. So we went from slope-intercept form to standard form. Oh, another thing about standard form is the coefficients are always integers. They're not going to be fractions. Standard form does not have fractions for coefficients. So that's why you got to get rid of the fractions if you have fractions. All right. Any questions how I went from slope-intercept form to standard form here for that linear equation? All right. We good on that problem there? Let's try another one. This is not classwork. This is another one I'll walk through. Suppose that we want to write the equation of a line that contains this point and has this slope. Well, how is this problem different than the one we just did up here? Well, the main difference is the fact that this point no longer qualifies as being a y-intercept like this one was up here. This problem is going to be a little bit more involved to find the equation for, as opposed to this one we just got done doing up here, because that was a nice y-intercept. This is not a y-intercept anymore. So let's just show ourselves how to find the equation of this line that contains this point and has this slope. Okay, let's go ahead and do that now. Let's see. So therefore, we know that the line must contain the point -4 and -2, and we are told that its slope has to be 3/2. Now, there's one of two ways you can do this problem, ladies and gentlemen. You can, I'll call this option A. Option A is you can use slope-intercept form to write the equation of this line. But in order to do so, we're going to have to know our y-intercept. We already know our slope, but we got to find our y-intercept. To find the y-intercept, we're going to have to just use this point that we're given. This point I'll generically call xy. If this point is to lie on our line, then this point must satisfy the equation that we're trying to develop here. That being said, I'm going to replace the y variable with the y coordinate of -2. I'm going to replace the x variable with the x coordinate of -4. And I'm going to replace the slope m with 3/2. Let's go ahead and make all these substitutions. What remains now is I got to solve for b, the y-intercept. So therefore, I'm going to have -2 is equal to, now what's this going to give us here? That's going to be -12/2. So -2 is equal to -6 plus b, add 6 to both sides, and b walks out with a value of 4. So your y-intercept is 4. Therefore, our equation is going to be y equal to the slope, which is 3/2 x plus b. B was found to be 4. We are done. That would be the equation of my line that contains this point and has a slope. Any questions how I found that equation? And we can just leave our answer in slope-intercept form there. Any questions how I just found the equation of that line that contains that point and has that slope? The way I did it is I used the slope-intercept form to do that. That's one way to do the problem. It's not the only way, though. Here's another way we could have done this problem. Option B, I'll call it. Option B is I could have used what is called point-slope form to derive the equation of this line. This is called point-slope form. Use point-slope form, I still need a point on my line, which is right here, -4 and -2. And I also need the slope of the line. Oh, we're given that too. So to write the equation of this line, all we have to do is, using this point and this slope, drop things in where they belong. So as far as this point-slope form equation is concerned, this is going to be the point x1, y1. So in for x1, I put -4. That goes in here. -2 drops in for y1. And m takes on the value of 3/2. So let's go. Let's write our equation. We got y minus y1, y minus -2. equal to my slope m, which is 3/2 times x minus x1. x1 is -4. There's your equation. But this equation's in point slope form. Suppose I want to get it in the slope intercept form and convince ourselves that we get the what? Same answer that we got up here, because we should. Okay, how do we do that? Well, we're going to solve this equation for y. Y subtract a -2 is y plus 2. X subtract a -4 is x plus 4. What I'm going to do is I'm going to distribute the 3/2 inside the parentheses. 3/2 times x is 3/2 x. 3/2 times 4. What's 3/2 multiplied by 4? It's going to be 6, correct? Finally, solving for y, I subtract 2 from both sides. And I get y is equal to 3/2 x plus 4. That looks awfully familiar, doesn't it, that equation? Because, ladies and gentlemen, that equation is the same as this one up here. And we understand the different ways we could derive this equation. You could derive it by either using slope-intercept form, using the point and the slope, or you can use what's called point-slope form to come up with the same equation. Any questions how I came up with that equation for that line that contains that point and has that slope? So there's two different ways. Now, on an exam or whatever, if I say, you know, find the equation of this line that contains this point, has this slope, frankly, I don't care what method you use. I just hope you come up with the correct equation. All right, time check. Where are we here? 1:24. Okay. All right, got that? Good on that? All right, let's try this next one here. Oh, ladies and gentlemen, I have the graph of a function in the XY plane. Suppose this graph is not a linear function, but rather a nonlinear function. It looks like this. Suppose I'll choose two unique points on this graph, right here and here. I'm going to designate this point here as being my point 2, 4. Drop a perpendicular down here, and that's 2. And I'm going to drop a perpendicular down here, and this point's going to be 416. Up here, 416. Okay. So this is a graph of some function in the XY plane. Suppose that I want us to compute the average rate of change of this function f of x with respect to x. So I'm calling this function not a function y. I'm going to call the y variable f of x instead. Doesn't matter what you call the input and output variables, by the way. We looked at that last week. So I'm going to try to compute the average rate of change of this function f of x with respect to x on this interval from 2 to 4. So the interval of interest is 2 to 4 here. That's the interval that we're interested in right here. So how do we do that? Well, the average rate of change of a function with respect to its independent variable, in this case x, on the interval from 2 to 4, geometrically speaking, is really going to be equal to the slope of this line segment here. The slope of this line segment, ladies and gentlemen, is going to be the average rate of change of f of x with respect to x on the interval from x equals 2 to 4. We call that the average rate of change. This line has a name. It's called a secant line. And that's something that you will run into in your first semester of calculus, what a secant line is. Okay? That's the secant line. So as it turns out, the slope of this secant line is equal to the average rate of change of f of x with respect to WRT with respect to x on the interval of 2 to 4 on this interval. Okay. So all we gotta do is find the slope of this line segment. Well, we got 2 points on the line segment, don't we? And the 2 points are 2, 4, and also 4, 16. That should be more than enough to compute the slope of that little line segment there, or the average rate of change of our function with respect to x on this interval. I'll call this point x1, y1, designate this as being my second point. Really doesn't matter which one you call your first and second point. And therefore, ladies and gentlemen, we're going to find the slope of this secant line. It's going to be y2 minus y1 over x2 minus x1, or specifically, based on how I define y, it's going to be f of x2 minus our function evaluated at x1 divided by x2 minus x1. See, because what this is, if you project this over the vertical axis here, this is going to be f of 2. You project this back horizontally, the vertical axis is going to be f of 4. Okay, f of 4, f of 2, and that's 2 and 4 right there. Okay. All right. So it's going to be f of 4 minus f of 2 over 4 minus 2. But what's f of 4? F of 4 is what? 16, correct? This is going to be 16 minus 4. F of 2 is 4 over 4 minus 2. So the slope of that secant line is going to be 16 minus 4 over 4 minus 2, which is 12 over 2, which is 6. So 6 is the average rate of change of f of x with respect to x on the interval from 2 to 4. Geometrically speaking, 6 is the slope of this secant line. It's the slope of that secant line segment. Okay. Any questions? How I computed the average rate of change of this function with respect to x on the interval from 2 to 4. That's called the average rate of change. Okay. So an average rate of change always involves an interval. In calculus, you're going to learn how to find what's called the instantaneous rate of change of this function with respect to x precisely at some value of x. For instance, if I wanted the instantaneous rate of change of f of x with respect to x precisely when x is equal to 3, well, ladies and gentlemen, geometrically speaking, that instantaneous rate of change of f of x with respect to x precisely at x equals 3 is going to be the slope of not a secant line, but the slope of something called a tangent line. And the slope of this tangent line that touches this graph precisely at x equals 3 is called the instantaneous rate of change of f of x with respect to x precisely at 3. That's called the instantaneous rate of change. Algebra deals with an average rate of change on some interval. Differential calculus can find you the instantaneous rate of change of a function with respect to x at some precise single value of x. Okay, algebra can't do that. But in order to go from the average rate of change to the instantaneous rate of change, you have to learn what the derivative is in calculus, and that's called differential calculus. The branch of calculus called differential calculus. And the instantaneous rate of change of a function from the average rate of change of a function is made possible by something called a limit, because the derivative and the antiderivative in calculus is based on the concept of what's called a limit. And so the first thing you run into in calculus 1 is you run into what limits are, okay, and how to compute limits of a function on a particular interval. All right. All right, any question how we computed the average rate of change of f of x with respect to x on the interval 2 to 4 here? It is 6, okay, for this function here. All right, we're done with that. Let's see what time it is now. Oh boy, okay. All right, so ladies and gentlemen, I'm going to show you how to solve an equation and an inequality using the graphing calculator. Okay, solve using a graphing calculator. Suppose that we have this linear equation, 2x plus 4 equals negative x minus plus 1. Now we could obviously just solve that, manually, because we've been solving equations like that for, it seems like eons now, correct? But I'm going to show you how we can solve it graphically using our calculator. To do that, I'm going to graph the left side of my equation. So on my graphing calculator, I'm going to let y1 be 2x plus 4. And then I'm going to graph the right side of my equation by letting y sub 2 be equal to negative x plus 1. When I graph these two sides of the equation, I'll have two lines graphed in my xy plane. And ladies and gentlemen, where these lines intersect, that point of intersection, okay, specifically the x coordinate of the point of intersection between these two lines is going to be the solution to this equation. Because it's going to be for this x value here, whatever the x value is, it's going to be for this x value whereby the y coordinates are the same, or where the left side of the equation is equal to the right side of the equation. That's where these y values would be the same for the x value we're about to find. And again, that x value is going to be the x coordinate of the point of intersection. So let's get on our graphing calculator and type this in our equation editor, type the left side in, type the right side in, and graph them and find that point of intersection. So we're going to go to our calculator here. I'm going to hit my on button. That might be helpful. And then go to y equals. And then I'm going to type in the left side of my equation there. And so what is the left side of my equation? Be 2x plus 4. So 2x plus 4. And y2 is going to be the right side of my equation, negative x plus 1. Now when we hit graph, normally the default setting for your x and y axis when you hit your window button should be from negative 10 to 10 by 1 on both axes, both the x and y axis. For the y, for the x min, x max, the spacing between tick marks on the x axis. Same thing for the y axis, y min, y max, spacing between y tick marks. If you hit graph now, you should see the graph of, there's the graph of the left side of your equation, the blue line. Here comes the graph of the right side of your equation, the red line. And where these two lines intersect, the x coordinate of that point of intersection is going to be the solution to that equation. Because it's at this point of intersection where the left side of the equation equals the right side of the equation as far as the y variable is concerned. So we got to find that point of intersection. So we go to calculate, second trace, takes us into calculate, and we go down and grab the intersect function. Hit enter. Your cursor will be sitting on one of your lines. We'll call that the first curve. Hit enter. The cursor bounces the other line. That'll be the second curve. Hit enter again. And ladies and gentlemen, the solution to that equation must be x equal to negative 1. X is negative 1. We just solved that equation graphically. So x is negative 1. And when x is negative 1, the left side of your equation would be 2, and the right side of your equation would be 2. That's why the solution to that equation is negative 1. X equals negative 1. Any questions how I solve that equation graphically?
When I click graph, it just says invalid DIM.
All right, if you go to your equation editor, just make sure up here that these stat plots are all turned off. Are they all turned off? In other words, you don't see like any reverse video on any of them, do you? Do you see any of this on any of these stat plots?
Do I see any of what?
Any of these stat plots turned on up here?
Only plot 1.
Yeah. What you got to do is move your cursor up to plot 1 and hit your enter button to toggle it off. Okay.
Okay.
So just move your cursor up to plot 1 and hit your enter button to toggle it off. It should now be off, looking like that. Now it should graph. All right, hit your graph button. You see them?
Yeah, it works.
All right, you were trying to graph those lines and also a stat plot, and there was a conflict with the scaling. All right, so any questions, ladies and gentlemen, how I graph the left side of that equation and the right side in the form of lines, and then we found the point of intersection. And that point of intersection, the x coordinate of that point of intersection is indeed the solution to that equation. X must be equal to -1. All right, so that's how you can graphically solve an equation. Graph the left side, graph the right side, look for the point of intersection or the points of intersection, and it's the x coordinates of those points of intersection that would be the solutions to your equation. That's pretty cool, huh? So you can graphically check your answers when you solve an equation. In a similar fashion, I could also solve an equation, an inequality using the graphing method. If I took the same one up there, that was an equation 2x plus 4, that was equal to -x plus 1. Suppose I want 2x plus 4 to be less than -x plus 1. That's to say, I want my left side of my equation to be less than the right side of my equation. That's to say, I want my blue line to be less than the red line. That's to say, ladies and gentlemen, that my blue line better be below the red line. And the red line must be above the blue line, okay? So we want to determine for what x values is the blue line below the red line, because that solution set will be the solution set to this inequality. So let's just go back to our graphing calculator and just take a look at that graph here. Oh, I can't believe I got to do this over again. Every time I close this out, I lose my information. Got to do this all over again. All right, here we go. Let's graph them. Now, what was that point of intersection again? I'm going to have to find it again. Whoops. So go down, use the intersect function. All right. Now, can anybody tell me for what values of x is the left side of our inequality less than the right side? In other words, can you tell me for what values of x is the blue line below the red line? Because the blue line is the graph of the left side of the inequality. The red line is the graph of the right side of the inequality. Can anybody tell me? X must be less than what number for the blue line to be constantly below the red line? X has got to be less than what? -1? For values of x that are less than -1, the left side of the inequality is below the graph of the right side of the inequality. If you put in values in an inequality that are greater than -1, no good, because then the left side of the inequality will be greater than the graph of the right side of the inequality. So the solution set has got to be x is less than -1. And we're done. We've solved it. So this inequality has been solved graphically. Interval notationally, the solution set would be that. Okay. There you go. All right, ladies and gentlemen, we got to skedaddle out of there. We got to get into applications of linear functions, or else we'll never finish. Okay, so section 2.5 is the last section here. It's entitled Applications of Linear Functions. All right, now to address this section, I'm going to go immediately into the textbook. I'm going to start looking at some problems. Okay? So we'll have to go to our textbook here. And I bet I know what I got to do. Wait a minute, let's see here. Might I be able to get lucky here? Let's see. No good. Got to log in again. It logged me out. Hold on. It times out for so many minutes of inactivity. So just bear with me. Okay. All right, so these problems are going to be coming out of section 2.5. I'm going to illustrate some of these. I'm going to go immediately to page 223, which is section 2.5. Yeah, this happened to me earlier in my face-to-face section, so forget that. That don't work. Section 2.5. All right, applications of linear equations and modeling. Ladies and gentlemen, I sincerely hope that outside of class, you are spending time to go through some of these valuable examples. Make sure you study these examples. It's only going to enhance your understanding of what's going on in the class, okay? Your author does a very good job in laying the steps out, all right? I would definitely invest time in looking at all these examples. Feel free to look at the rest of the section if you want to, if you want to solidify things, all right, in your mind. I know our schedules are busy and all that. We got all these things going on. But if you really want a firm understanding of this course, taking some time out, investing that time and looking through some examples is really going to enhance your understanding of college algebra. All right, let's go down on page 223 and look at problem number 52. There's loads of extra practice problems in here, and I do give you the solutions to the odds and the evens. So there's no excuse to go in here and do some extra practice if you want it. It's waiting for you. All right, I'm going to try to demonstrate number 52 here. At a parking garage in a large city, the charge for parking consists of a flat fee, I like to call a fixed fee, of $2 plus $1.50 per every hour you park there. A, write a linear function to model the cost for parking P of T for T hours, and B, evaluate P of 1.6 and interpret the meaning in the context of this problem. So for 52, problem 52A, the total cost for parking in this garage is going to be a fixed cost of $2. Plus a variable cost, which is going to be $1.50 per hour times T hours. I'm going to spin this around and put this in slope-intercept form. Now this linear function is in slope-intercept form. Can anybody tell me what the slope of this function is? What is the slope? What would be the slope of this line here? This linear function.
150.
All right, so the slope M is $1.50. Now, can we, in plain English, explain what this slope is really saying? What is it really saying? Remember, a slope is a rate of change. It's a rate. So how would we express this as a rate? What's it saying? Anybody?
3/2.
Yeah, 3/2. Or we could just leave it like this and say that for every hour that we park in this garage, we're going to be paying $1.50. Do you agree? So this is the rate with which the cost is increasing per time that we leave our vehicle in the garage. So $1.50 per every hour. That's what this slope really means. That's the rate we're being charged every hour for parking there. What's the y-intercept? And what does it mean? How do we interpret what it's saying? What's the y-intercept?
It's 2.
All right, $2. And well, how would you interpret what that's really saying? The y-intercept here. See, if we were to graph this relationship here, our vertical axis is the cost, P of T axis, and the horizontal axis is the time axis. Our y-intercept is up here at $2, and then our slope is positive 1.5. So the graph of this linear function that models cost versus time would look like this. Can anybody tell me the significance of what 2 is saying there? At what time does 2 occur? At what time does 2 occur? It's our y-intercept. So it occurs at time t equals what? 0. So what this is saying is when we first pull into that garage at time t equals 0, we're going to have to lay out a what? a cost of $2. That's just to get into the garage, $2. Call it an entrance fee, okay? So P of 0 is going to be equal to $2. That's what it is. It's just an entrance fee, okay? That's the fee you have to pay just to get into the garage there. Now, using that function we developed in part B, they want us to find P of 1.6. To do that, it's pretty simple. You just replace time T with 1.6. So this is going to be $1.50 per hour times 1.6 hours plus $2. All right, get on your calculator and dial this up. Tell me what you get. How much are they going to charge us for parking into this garage for 1.6 hours? I can remember this from a morning class. I think it came out to $4.40. Is that correct? Anybody get that? That's how much it's going to cost to park there for 1.6 hours. And 0.6 of an hour is really 0.6 times 60 minutes per hour. So 0.6 times 60 minutes per hour is really what? 0.6 of 60 minutes is going to be 36 minutes. So if you park in this garage for 1 hour and 36 minutes, they're going to charge you $4.40. That problem make any sense there? Any sense? No, any sense? No pun intended. Did it make any sense? Okay, that's a classic problem involving cost. All right, that's problem number 52 on page 223, section 2.5. Let's go look at another problem, number 56. All right. Number 56. For these problems, they want you to do all 4 parts here, A through D. They want you to write a linear cost function that represents the cost C of X to produce X items. B, write a linear revenue function that represents the revenue R of X for selling X items. C, write a linear profit function that represents the profit P of X for producing and selling X items. And D, determine the break-even point. So this is a problem that you would probably run into in maybe a business class or an economics class. Okay, so problem number 55 here. Let's take a look here, number 55. Notice for 55, they give us a fixed cost. And the fixed cost is $2,275. They give us a variable cost. And the variable cost is $34.50. And then they give us the price at which an item is sold. And that's going to be $80. $80. $80. All right, so given that information, first of all, they want us to write a cost function. So if I manufacture X of these items, whatever they are, the cost of manufacturing X items is going to be equal to what? Well, ladies and gentlemen, we have a fixed cost that we have to realize. Got to lay out that $2,275, regardless of the number of items we produce. Plus you have a variable cost, which says this is $34.50 per what? Per every one item. And we're going to manufacture X items. So this is going to be $34.50 per one item times X items. This is your cost function. Spinning this function around. And here's your cost function. Any questions how I developed that cost function there? That's the cost of manufacturing X of these items. You have your variable cost and you have your fixed cost or your flat fee. Okay. So that's the answer to part A. That's your cost function. Now part B, they want a revenue function. Now cost is money we lay out. Revenue is money we bring in. Okay. So how much money are we going to bring in if we sell X of these items? Anybody? How much are we charging per item? How much revenue are we going to bring in for every item that we sell? Well, according to what we got there, looks like what? How much money? It's like $80. So we're going to bring in $80 or 80x dollars. That's your revenue function. That's B. Now in part C, they want us to write a profit function. I don't know if you're aware of this or not, but profit, ladies and gentlemen, is always equal to the amount of revenue you bring in minus the amount of cost you have to outlay. So our profit function, P of X, is really going to be equal to a brand new function called R minus C of X. Well, here's the algebra of functions here. This is really going to be our revenue, R of X minus C of X, our cost. So our profit is going to be our revenue, which is 80x, minus our cost function, which is to say 3450x plus 2275. Or it's going to be 80x, distributing the negative sign inside the parentheses, minus 34.50x minus 2275. What's 80 minus 34. What's 80 minus 34.50? It's going to be 4550. And then we're done. We have our profit function. This will give you the profit that you will realize when you produce and sell X items. This is the profit you're going to bring in. That's your profit function. Finally, part D, they want to know what is the break-even point. Does anybody want to help us out here? What does it mean in business to break even? To break even. The almighty break-even point. What does that mean? To break even means to do what? To break even. Well, you know, to break even, do we make any money? Do we lose any money? Well, when we break even, we are not making any money, but we're also not losing any money. We broke even. So to break even means that the revenue has got to be equal to the cost. That's what it means to break even. Revenue equals cost. And so therefore, we're going to take our revenue function and we're going to set it equal to our cost function. And then, ladies and gentlemen, by doing this, we're going to have to solve this equation for X. Now you can do that graphically using your calculator. Graph this left side of the equation for Y1. Let Y2 be the graph of the right side. Find the point of intersection between those two lines. And the X coordinate of that point of intersection will be the solution to this equation. That's the graphical way of solving it. Or you can just solve it the way we solved it way back in elementary algebra. So just going through this, solving this here. We're going to have our what? 45.50 X, and that's got to be equal to 2275. So to solve for X, we take 2275 and we have to divide that by what? By 4550? So what is 2275 divided by 4550? Is that right? Is that right there? X is equal to 50. And so later on to break even, we have to manufacture and sell 50 what? Items. That's how we break even. You got to manufacture, you got to produce and manufacture, you got to manufacture and sell 50 items to break even. Now, what I want you to do is I want you to graph the left side of this equation right here and graph the right side. And let's see what that point of intersection is between these two graphs here. So go ahead and graph both sides of that equation in your calculator. Now, you might not see these graphs because we have a big problem here. The big problem is that the second equation has a y-intercept of 2,275, and that is a major issue. And so we're going to have to go to our window setting. We're going to have to tweak the setting on our axes here. We won't even see the graph. I'm going to go further out on my x-axis. I'm going to go out to 100 on my x-axis. And my y-axis, I'm going to go up to I'm going to go up to about 3,000. I'm going to space my tick marks on my y-axis, not just 1 unit apart, but I'm going to space them like 100 units apart too. So I'm going to go with this scaling here. Hit graph now, and let's see what we can see. There's the graph of your revenue function. Here comes the graph of your cost function. Well, it looks like they're going to intersect each other, but we got to go up higher with our screen to see the point of intersection. So I got to go back to window, and my Y max value's got to go up higher. I got to go up to maybe about 5,000. Hit enter, hit graph rather, and let's see what we're looking at now. There's the graph of the left side, the revenue equation. Here comes the graph of the cost function. Now, what's the point of intersection? That point of intersection is called our break-even point. So to find it, we go to calculate, second trace, use the intersect function. And there you go, ladies and gentlemen. We can see that if we manufacture and sell 50 items, we will break even, where our revenue will be $4,000, but our cost will also be $4,000. That's where we break even. So I have a question for you. Do we have to sell more than 50 of these items or less than 50 of these items to make a profit? Anybody?
More.
More, because when X is greater than 50, notice your revenue function, which is the blue graph, is above, okay, or exceeds the red graph, which is the cost function. So you are correct. We have to sell more than 50 of these items to experience a positive profit. If we sell less than 50 items, then our revenue will be less than the cost and our profit will be negative. And that means we're well on our way to going out of business. Okay. Is that making sense here? All right. So, it's nice to have a happy marriage between your calculator and the manual way of doing things. I hope that, you invest some time in learning how to graph a couple of these things and playing around with the graphs a little bit. All right, let's try number 61 here. Here we go. We're going to look at this problem. The data in the graph shows the wind speed Y in miles per hour for Hurricane Katrina versus the barometric pressure X in millibars. And the source is the National Oceanic and Atmospheric Administration, NOAA. Okay. We collected some data points here. In fact, there's quite a few data points here that have been plotted. But, you can see that we have what's called an inverse or indirect variation between atmospheric pressure of the storm and the wind speed that's sustained probably around the eye wall of the hurricane, I would imagine. Of course, I'm not 100% sure on that. But anyways, you can kind of see that as the pressure rises in the center of a hurricane, the wind speed decreases. And that makes sense because if the pressure rises in a hurricane, that means the hurricane is weakening, okay? And therefore the wind speed drops off in accordance with that. If the atmospheric pressure deepens or decreases, that means the storm is getting stronger. And for that reason, the wind speed would increase. Okay, so this is an inverse variation that exists between pressure in a hurricane center and also the wind speed. Pressure increases, wind speed decreases. Pressure decreases, wind speed increases. That's called an inverse variation. All right, notice they want us to write the equation of a line, okay, that contains these 2 points, 950, 110 and 1000, 50, where again, the x-coordinate is the what? The x-coordinate is the barometric pressure in millibars. The y-coordinate is the wind speed in miles per hour. I have a question for you. Do I have enough information to write an equation of a line given 2 points on the line? Do we have enough information to do that, ladies and gentlemen? Think we can do it? We got 2 unique points. We should be able to write the equation of this line. Let's do that. So to write the equation of this line using those 2 provided points, first I have to find the what of the line. Anybody? What do I got to find? First thing. Got to find the what of the line. I have got to find the what? The slope of this line. So we're going to use our slope formula. So therefore, y2 is going to be 50 miles per hour minus y1, which is 110 miles per hour, divided by the change in pressure. So we have the change in wind speed versus the change in pressure. That's to say 1,000 millibars minus 950 millibars. Therefore, when you work this out, you get negative 60 miles per hour per 50 millibars. How do we explain or describe what the slope is really saying in the context of our problem? Anybody want to, in plain layman's terms, indicate to us how to express what this is saying? What's that slope really saying? The rate of change of wind speed versus pressure, agree? So how can we interpret what that's saying? Well, a way to interpret this is to say that the wind speed decreases by 60 miles per hour per every 50 millibar rise in pressure. And we can even reduce this down by 10 and take it down to negative 6 over 5. So an equivalent way of discussing this slope is to say that the wind speed decreases 6 miles per hour per every 5 millibar of pressure rise. So when the pressure rises 5 millibars, the wind speed drops off by 6 miles per hour. That's how you can, relate to what the slope is really saying in the context of our situation. None of these are y-intercepts. And so, ladies and gentlemen, to write the equation of this line, I'm going to use the slope-intercept form, y equals mx plus b form. And I'm going to choose a point. I'm going to choose maybe 951.10 as my point. Therefore, if this is a point that sits on the line whose equation we're trying to write, it must satisfy the equation. That's to say, I'm going to replace the y variable with 110, x variable with 950, and the slope is replaced with negative 6/5. Just make our substitutions, drop everything in where it belongs. And now we got to solve for the y-intercept b. Now, what's negative 6/5 times 950? I believe that's negative 1140. Adding 1140 to both sides of the equation, the y-intercept b walks out with a value of what? 1250. Therefore, we can write the equation of this line that relates atmospheric pressure and wind speed of this storm. So y is equal to the slope, which is negative 6/5 times x plus the y-intercept, which is 1250. There's the equation that they wanted us to write in part A. So therefore, x is the pressure, atmospheric pressure in the center of the storm, and y is the sustained wind speed around the center of the storm. This linear function relates those two variables, okay? Now, the point of this is we can use this equation to make a prediction. For instance, what if a hurricane has a center pressure of 800 millibars? What would be the predicted wind speed? Well, we'll let x be 800 millibars. And then we're going to have to solve for the wind speed y. So therefore, y is going to be equal to negative 6/5 times x, but x is replaced with 800 millibars plus 1250. All we got to do is go through and crank this out, and we'll have the wind speed. So the predicted wind speed for a hurricane that has a pressure of 800 millibars would be what?
$290.
290 miles per hour. That's an extremely strong hurricane here. Let's go back to our graph and see if that seems about right here. 290 mile an hour winds. That's likened to like an F5 tornado. Usually hurricanes are not as strong with wind speed as a tornado is. You go to 800 millibars, 800. Well, that's 850 millibars. Well, that's about right. Because look at, you can kind of see here that this is going back upwards this way. Do you agree? By the time we get to 800 millibars would be down around in here. So you can see that, yeah, that's going to be about what? Maybe about 290, correct? On the wind speed, that's going to be up here, right about up in here for 800 millibars. 800 millibars is about right, right here. So, according to this relationship, that's what it's looking like it would be. Okay, so that seems plausible. Based on the graph, it does. But normally you're not going to run into 250 mile an hour winds for a hurricane. 180 mile an hour winds, even 200 mile an hour winds is very, very extreme for a hurricane. All right, what time is it? 2:12. Okay, ladies and gentlemen. For your last classwork today, we're going to have you do problem number 62. Caroline adopted a puppy named Dodger from an animal shelter in Chicago. She recorded Dodger's weight during the first 2 months. The data in the graph show Dodger's weight, Y in pounds, X days after he or she is adopted. I'm not sure. After the puppy's adopted. Okay. Now, the horizontal axis is the number of days since adoption. So day 0 is the day that Dodger came home. That Dodger was adopted. The vertical axis is the weight of the puppy in pounds. They give you two different points on this graph. I want you to do parts A, B, C, and D. I want you to do parts A through D. Okay, this will be the last classwork there. Parts A through D, problem 62. That's their last classwork. Go to it. I'll give you time to work on that. Let's take a look here. So for part A, they want you to, using these 2 points on the graph, write a linear function that models the days since adoption versus the weight of this puppy. The first thing I do is find the slope. The slope is 11 pounds per 40 days, and the interpretation of this slope is for every 40 days after adoption, the puppy puts on 11 pounds of weight. This happens to be a y-intercept, which makes our life really easy to write the equation of the relationship here between weight and days since adoption. This would be the linear function. The y-intercept is 11. The y-intercept represents the initial weight of the puppy at the time of adoption. Day x equals 0. That was the day that Dodger was brought home, and the initial weight was 11 pounds. To achieve a weight of 90% of its full-grown weight of 70 pounds, you take 90% of 70, which is 0.9 times 70, which is 63 pounds. To find how many days after adoption the puppy will attain that weight, you just let y be 63, and then you solve for x. So now we set y equal to 63, solve for x, and we determine it's going to require about 189 days. 189 days after we adopt Dodger, Dodger should reach a weight of about 63 pounds. All right, anybody get those results there?
Yes.
All right. Well, that's it, ladies and gentlemen. I'm all out of time, and I will update Alex to open up these sections that I've gone over. Please try not to fall behind. Try to stay current with the homework, and all shall go well. Okay. All right, I'll stay on the line if you have any other questions. If not, have a great day.